Japan is a geographically small nation, but it is responsible for a massive defensive perimeter. This map shows the country's Air Defense Identification Zone, or ADIZ, a vast expanse of the Western Pacific where Japanese airspace must be monitored and protected. Defending a zone of this scale against rapidly modernizing neighboring air forces requires high-end, long-range interceptors capable of sustained air superiority. By the late 1990s, the primary aircraft fulfilling that role was the Mitsubishi F-15J. While highly capable, this fleet was beginning to age, and its airframes were approaching the physical limits of their upgrade potential. Japan's original solution was straightforward: purchase the American F-22 Raptor, then the undisputed king of air-to-air combat. That plan was halted by the 1997 Obey Amendment. The U.S. Congress legally banned the export of the F-22 to protect its sensitive low-observable and sensor technologies from being accessed by any foreign power. This legislative barrier left the Japan Air Self-Defense Force without a viable fifth-generation successor that met its specific requirements for high-end air dominance. The U.S. denial of the F-22 acted as a severe catalyst, leaving Tokyo with no choice but to revive its domestic aerospace sector and engineer a sovereign successor from scratch. By 2009, the Japanese Ministry of Defense shifted its focus toward a domestic future fighter program to replace the aging F-2. A 2010 report defined a conceptual blueprint for a jet designed to leapfrog current technology, titled the I-3 fighter. The first I stands for informed. This architecture shifts the focus away from standalone radar toward a networked system where the fighter gathers and distributes data from drones, satellites, and other allied platforms. The second I is intelligent. This required advanced AI flight assistance and flyby optics to process that influx of battlespace data instantly, assisting the pilot with prioritized targeting. The final I stands for instantaneous. This defined a requirement for rapid response lethality, establishing the framework to eventually carry directed energy weapons. This theoretical I-3 concept became the engineering baseline for what would officially be named the Mitsubishi FX program. The FX was designed to be a technological jump over the platforms that Japan's allies were unwilling to share. Mitsubishi Heavy Industries was selected as the prime contractor, tasked with turning the I-3 concept into a physical airframe. The first step was the X-2 Shinshin technology demonstrator, which completed its maiden flight in 2016. The X-2 proved that Japan could indigenously manufacture radar-absorbent materials and 3D thrust factoring control systems. To reduce the massive costs of physical prototyping for the full-scale fighter, Japan shifted its development to the Digital Model Unit, or DMU, series. The 23 DMU iteration focused on establishing a baseline low-drag stealth shape, utilizing aerodynamic, high-aspect ratio wings. In the 24 DMU phase, engineers iterated on the internal weapons base, attempting to maximize payload capacity without creating a larger radar cross-section. The 25 DMU phase refined the fuselage to accommodate the developing IHI XF9 engine, resulting in a slimmer aerodynamic profile. Development concluded with the 26 DMU, finalizing a heavy twin-engine profile optimized for long-range Pacific patrols. These digital iterations allowed Japanese engineers to validate complex stealth geometries and internal bay designs, significantly reducing the requirement for a long series of physical prototypes. A stealth fighter engine must produce overwhelming thrust while maintaining an incredibly narrow diameter to reduce its radar signature. Japan's solution was the XF91 turbofan engine, developed by the ATLA and IHI Corporation. This diagram compares the XF91 to the F110 engine used on Japan's F2. The newer engine achieves a 30% smaller intake cross-section. Despite its slim profile, the engine generates over 15 tons of wet thrust with afterburners, achieving a high power-to-weight ratio. To reach this power level, the turbine inlet must withstand 1800 degrees Celsius, a feat made possible by Japanese fifth-generation single-crystal superalloys and ceramic matrix composites. Beyond propulsion, the engine functions as a major onboard power plant, generating 180 kilowatts of electricity. For the twin-engine FX, this yields a total of 360 kilowatts of onboard electrical capacity. This electricity is vital for powering the aircraft's massive AESA radars and the next-generation electronic warfare suites defined in the I-3 vision. The success of the XF-91 proved that Japan had mastered the metallurgical and thermodynamic hurdles required for sixth-generation aviation. While Japan possessed the technical pieces, the projected $40 billion cost of producing a sixth-generation platform alone became a major financial burden. Sensing this strain, the United States offered a joint project, a hybrid airframe merging the designs of the F-22 and the F-35. Tokyo rejected the offer, choosing to walk away from proven American platforms. At the heart of this rejection was a requirement for freedom of modification. Past joint ventures with the U.S. often left Japan without access to the aircraft's core source code, making them reliant on Washington for every software update or weapon integration. Japan realized that technical sovereignty is only possible if the nation controls the administrative keys to its own aircraft software. In December 2022, Japan officially merged its FX program with the UK and Italy's Tempest project to share costs while maintaining that vital sovereignty. This created the Global Combat Air Program, or GCAP, which aims to have a sixth-generation fighter in service by 2035. The GCAP architecture conceptualizes the fighter as a central node within a system of systems, a network extending beyond the single airframe. The manned fighter acts as a coordinator for autonomous, loyal Wingmen drones directed into contested airspace to scout and strike. AI will synthesize data from allied ground sensors and the drone fleet, projecting a unified, high-fidelity view of the battlespace to the pilot's helmet. This partnership also marks a diplomatic milestone, building a transatlantic Pacific alliance that diversifies Japan's security ties away from total dependence on the United States. The denial of the F-22 in 1997 was intended to restrict the proliferation of high-end stealth. Decades later, that same policy has forced Japan to become a lead systems integrator, permanently altering its role in the global aerospace industry.